is former director of the NASA Software Engineering Center. Mike Hinchey is very much interested in formal methods and published a couple of books on system specification and design, and that's also the link to Wolfgang Weisig, who made you come here today somehow. So I think that covers at least a few important aspects, and I'm very much interested in your talk.
Thank you. Well, as you say, I'm a bit of an outlier to this event, and I'm much more in Wolfgang's area, dealing with formal methods, system specification, and so on. And in that context, I was running a research center devoted to that topic in Australia when President Clinton appointed me to NASA as an exceptional appointment. The deal was I was supposed to stay for 4 years and introduce formal methods to NASA. And at the end of 4 years, they decided it would be illegal for me to stay, so they changed the law. And President Bush reappointed me, and then President Obama reappointed me. And long story short, I stayed 15 years instead of 4. But over that 15 years, of course, I was still working in the area of formal methods, but I was becoming much more interested in autonomous systems, and in particular in self-managing systems, and I'll explain why that context is important. But essentially all of this is based around software, and as you can imagine, most space missions involve expertise in all sorts of areas, from physics and biology and chemistry through to engineering, through to software, all sorts of areas, bringing together lots of people. So every mission is a huge concerted effort. And I should remind you that most NASA missions take in the region of 20 to 30 years in the planning. So when a mission is launched, most of the people who worked on it have retired or possibly even passed away. So it's a very process, it's a very large task. But I'd like to remind you again that the role of software in all of this. And I'd like you to sort of think just for a minute how much we've done in the last 25 years in software. And a lot of that has been because of the internet. And it's not that we had the internet, it's that we gave people access to the internet. And it was easy to be able to use the internet. So I'd like to just ask you to, for a minute, continuing William's idea of a little bit lighthearted in the morning towards the end of the week, I'd like you to imagine for a minute what software and computing might be like in the future. So I'm not sure, I think most people here are from Germany or Greece. So do you have Antiques Roadshow on TV? What? Antiques Roadshow, do you know this program on TV? No. Okay. It's a program on BBC, and there's an American version, and I believe multiple other countries have a version. And the idea is that you find junk around your house, or you buy it at a market, and you don't know what it is, and you don't know what it's worth. So you bring it to these experts, and they look at it and they evaluate it. Okay? So you have a similar sort of program? Okay.
No, we don't have, but now you describe it, I've heard of it.
You've heard of it, okay. Well, actually, my two favorites are, I actually know somebody who went on it one time. He found a painting, a large painting in his father's attic when his father died. And it turned out to be an original Van Dyke. So it was worth an absolute fortune. So he did really, really well. But my favorite is somebody I don't know who went to the program, and she went to the expert, and they had this Ming vase. And she said, I bought this at the Great Wall of China 5 years ago. And I was so lucky because the guy just dug it up that morning, and there was still mud and dirt on it. And the expert said, yes, there was mud and dirt in it when he dug it up that morning because he buried it the night before. And it's worth about $1.50. Okay, so anyway. This is an example of what computing might be like in the future.
Here we are in Cincinnati for another edition of Antiques Roadshow, celebrating our 1008th year on public television. Let's take a look at what people have brought us today.
Want to tell me a little bit about this? I found this next to some crappy old gold bullion at a swamp matrix, and I didn't know what it was, but I thought it was pretty, and I have it prominently displayed at my home in a hover hutch.
Aha. Care to take a guess at what it is?
Well, my robot husband thinks it might have been an old head energizer.
No, this is a primitive version of the computer.
You mean like the thin chips we have in our tongues?
Exactly, but unlike the thin chips, which perform billions of functions, these were only used for storing porn. Which led to the great porn dynasty that ruled from 2012 to last year. Care to take a guess at how much this is worth?
Well, I only paid 7 million rupees for it.
Aha! You paid 7 million rubiks too much. My suggestion, beam this right into the disposal cube. These pieces of crap crashed and froze so frequently people became violent. We'll be right back with more Antiques Roadshow after this 8-hour pledge drop.
Well, let's not be too facetious. But think back how far we've come in a very short period of time. This was the state of the art in 1949, and there's a reason I picked this particular machine. It's called EDSAC. It was built at the University of Cambridge. And it wasn't the first computer by any means. It wasn't the first electronic computer, but it was the first computer to store store a program in memory that could be altered as it executed. Okay, and this made it very, very unique at the time. But more importantly, it meant it led the way for the future, where we could have software that adapts as it executes. I was lucky enough to know the people who actually built this and had some interesting conversations with them over the years. Just to give you an idea of what the state of the art was, 650 instructions per second, 1,024 17-bit words, paper input and output as you'd expect, 3,000 valves, 12 kilowatts of power, and it occupied a room of 5 meters by 4 meters and needed about 4 times that space around it just for ventilation. Okay? In 1951, so 2 years after this first ran, the British government conducted a survey, and they decided they would only ever need 3 of these machines. Okay? 3. And part of the reason for that was that they were only looking at using it for scientific purposes. But if you've got one of these in your pocket, you've got tens of thousands times more power in your pocket than 3 of these would be. It wasn't in 1958 that the first use of a computer for business came along. I'm the chair of IEEE UK and Ireland, and we're going to commemorate next year the first use of a computer for business. Any idea what the first use of a computer for business was? Lion's tea. Okay, so they did inventory of the tea that they were importing from India. And that was actually the first use of a computer for business. This is often, excuse me, this is often considered by people to be the first computer. It's the difference engine built by Charles Babbage. Most of you will recognize his photograph. Just to give you an idea of how big it is, the gentleman on the top left is taller than me. He's Doran Swade. He's the former curator of the London Science Museum. It's thought that if Babbage had access to fabrication technology like we have now, if he could have built the cogs and wheels with much more precision, then the machine that he built would actually have worked. He never actually finished it, but he did build a large chunk of it. I borrowed it once in 1994. I borrowed this from the Science Museum and I brought it to Cambridge for a conference. And the conference was on the 45th anniversary of the EDSAC meeting, which many people consider to be the first computer conference in Europe. And we had Maurice Wilkes, who ran it, as our after-dinner speaker. So we borrowed this machine from the Science Museum, and the morning of the conference, I got a phone call to say, "You do have insurance, don't you?" And there was a little bit of a panic. We called Lloyd's Register, who were the people who would insure this sort of thing, and they wanted £1 million to insure it for one night. We discovered by luck that if 2 of the museum staff came with it, it was covered by their insurance. So they were invited for dinner. It was well worth inviting them for dinner. But people don't understand why Babbage built this machine. A lot of people think, oh, Babbage set out to build the first computer. He didn't. He set out to solve a very, very specific problem. And the problem was that the logarithmic tables used in the shipping industry were notorious for the errors they had in them. So you can see here there's a correction in 1832, and a correction of the correction in 1833, and a correction of the correction of the correction in 1836. And this was commonplace. And as a result, ships were lost, cargo was lost, lives were lost. Okay? And as basically you could say it was a safety critical application. So Babbage's idea was that if you could calculate these numbers automatically and with precision, and then if you could print them out, and he actually had the idea of using brass cogs with numbers in reverse that he could press against paper and then spread ink across. So he actually had the idea of a printer. Then he would be able to solve this problem. This lady is often considered to be the world's first computer programmer. We call her Ada Lovelace. She was actually Augusta Ada Byron, then she became Augusta Ada King when she got married, and finally she became the Countess of Lovelace. So we know her as Ada Lovelace. But she was obsessed with this machine, and she felt it could do an awful lot more than just what Babbage was planning to do with it. And she had learned mathematics from the Morgan, so she was an educated lady, and she tried to do lots of different things with this machine, and she succeeded. And she would write down pieces of the programming that she did of the machine and put them on pieces of paper, and then would shuffle these pieces of paper around, and so on. So she actually came up with a lot of the ideas that we have nowadays, and that we use nowadays in computer programming. So she truly was the world's first computer programmer. And we try and promote this to young girls when we're doing our outreach activities for STEM. But I'd like to show you a chart from NASA, which each of the red dots represents a NASA mission, and the names are missing just because it makes it easier to read. But just to give you an idea, the one nearest to the center is the Hubble Space Telescope, and the one just to the left and below it is the Space Shuttle. It doesn't really matter what they are. But what this shows is that when NASA puts effort into its requirements of, say, 15%, it has a cost overrun of somewhere around 10%. When it has an investment in requirements of about 3%, it is a cost run of around about 200% overrun. This chart comes from the NASA Controller's Office, so the Chief Financial Officer of NASA. I'm sure the figures are mostly correct, but I believe the curve should be up and to the right, because the typical NASA mission overruns by about 800%. Okay? And if you consider that the mission to go to the moon in advance of going to Mars has software estimated at $8 billion US, only for the software. Think of what that cost overrun can be. So we're looking at building space exploration missions that can be resilient, so that they can survive in space over long periods of time. The oldest software in the world, of course, is Voyager, which has gone interstellar. But it's important that we have complex systems that we need to build, we need to be able to send out into space. And these are some of the most complex applications that we've ever built. They're certainly some of the largest systems we've ever built. They have, by their nature, to be autonomous, and I'll explain a little bit why in a minute. But there's huge consequences for failure. First of all, huge loss of investment in terms of cash, 20 to 30 years in the planning, which is lost, and the serious problem is loss of reputation, both with the government, who are going to be deciding on the funding, and the public, whose support is needed to make sure that the funding is there and available. So we've been looking at how we can use swarm technologies. So the idea is to be inspired by nature, not to copy it directly, but to be inspired by the idea of having flocks of birds or swarms of bees or shoals of fish. And this is being used in many, many areas. I have a colleague who works in Johnson & Johnson, and he claims that they can bring drug discovery times down from about 17 years to about 3 using swarm-based search. It's used widely in communication systems, particularly in things like on-demand TV and on-demand video. It's used by NASA a lot in environmental monitoring. People think of NASA as a space agency, which of course it is, but it spends about 70% of its budget looking at and examining the Earth and understanding how the Earth works and how many of the issues that we have with the Earth and survival of the Earth and of nature can be dealt with and addressed. And of course, for exploration, and this can be things like mining. I was with a colleague the other day. Rio Tinto have the largest robot in the world because it's the size of a 2-story building. And it's used in mining, but of course we want to use things that are much more flexible than that can move around much more easily, so we tend to use a large number of smaller devices rather than something large like that. But exploration can be under the ground, under the sea, in caves, in caverns, and of course on other planets, which is really where we're interested. So we're interested in using a large number of small spacecraft, and there's a number of advantages to this. First of all, solar power. Power is a big issue in space. NASA set up a prize about 25 years ago, offering $1 billion for anyone who could develop a battery that would run for 12 hours, charge for 12 hours, run for 12 hours, and so on indefinitely. Nobody's been able to do it, okay? Because we have memory loss in batteries, so every time you recharge, you have a slightly smaller amount of time of the charge left. It may only be milliseconds less, but the point is that it's degrading, and that's a big, big issue. So we have to use solar power, we have to use it effectively, and that becomes a problem. It's also a big problem for large devices, like, for example, the Hubble Space Telescope, which I'll talk about towards the end. We want to be able to go to places you can send a large device. So in mining, you can send a 2-story robot into a large cavern, but you can't send lots of other places where you want to find specific items and small items. We can do more complex things by coordinating, by getting devices to work together, and it's a lot easier to do that with smaller devices than with larger ones, and that gives us greater accuracy and greater flexibility. But most of all, it gives us resilience. It gives us an opportunity to keep something going. So if you think of a mission that's based on a single rocket, if we have a collision, the rocket's gone. Okay? Not necessarily completely gone, but damaged in some way, and probably not much use to you. If you send a number of devices, even if there are collisions, you won't necessarily lose everything. So we've been working for the last 20 years or so, and that, which means we're still about 10 years away from launch, on the autonomous nanotechnology swarm. And this is using a swarm, and we call it a swarm, but it's more like a flock of birds, to be honest. A swarm of spacecraft that can go to various locations in space and collect lots of data for us and do it quickly. So the first one, it's got 3 submissions. The first one is LERO, so the Lunar Amorphous Rover Antenna. So the idea is to be able to go to the surface of Mars and collect data, the surface of the Moon and collect data. This mission would collect in a day what the Mars rovers collected in totality. Okay? Now, obviously, they were far more successful than expected, but this mission could collect all that data in one day. There's a mission to go to the rings of Saturn called SARA, and the more interesting one and the more complex one, and the one I'll use for my example, is PAM, which is the Prospecting Asteroid Mission, and that's to go to the asteroid belt. And that's become a more important submission at the moment because NASA has a goal to put a human on an asteroid, so therefore we want to know a lot more about the asteroid belt. And currently we don't have a good model of the asteroid belt. As you probably know, it's hundreds of thousands of asteroids. The smallest is roughly the size of a tennis ball. The largest one that we know of is about 190 kilometers wide, so they vary greatly, and we do not have a good mapping of their path. So we don't know exactly where they are at any given time. And that's why getting to them and finding out about them is quite tricky. So we're using these sort of devices. We call them tech walkers. And the idea is that it can expand out, and it moves by basically falling over. Each of the nodes is a computer, and basically you transfer control from one computer to the next. And then by falling in specific ways, you can go over rocks, you can go over craters, you can go over rough ground.
Do they also generate energy in this way?
No, not at the moment. It's using a small solar panel, which isn't clear on this. This is obviously an animation, which I sometimes get complaints about, oh, that's only an animation. Well, here's the real thing. Doesn't go quite as smoothly. This is not as smooth, well, first of all, because gravity is different, but also it's metal as opposed to carbon nanotubes, which is what we use in space. So there's a big difference. But the principle is the same. It can shrink down to be a 30 centimeter cube. It can expand out to be 2 meters tall, and it can climb the outside of a 5-story building. So the other thing is we can put dozens of these together to make a sort of caterpillar, and they'll be able to carry devices and so on. So our PAM mission, and we call it a concept mission because it hasn't launched yet, and probably, given that we have approximately 10 years to launch, we're going to improve a lot of things over time. The mission concept is to go to L1, which is the Earth, Moon, Lagrangian point. It's a point in space where there's virtually no gravity on small bodies. And then to launch 1,000 spacecraft into the asteroid belt. They will be pulled solely by gravity, bringing them out to the asteroid belt, taking about 2.5 to 3 years to get there. And then when they get to the asteroid belt, they will self-organize into subswarms, groupings. And these will be based on the devices that they have. So each spacecraft will be the same, except they'll all be equipped with some sort of special device. So some will have cameras, some will have X-ray devices, some will have magnetic probes, etc., etc. These will all be roughly the size of a laptop, similar weight to a laptop. So they're similar to what I just showed you, but these will fly instead of falling over. And they can only fly with the pull of gravity or tiny amounts of propulsion. So they can use tiny little jets to get them moving a couple of centimeters at a time. They will work completely autonomously in the asteroid belt and collect data, and then send that data back to Earth. Now, NASA requires by law that an astronaut is involved in any autonomous mission. The astronaut will sit on Earth and will have a sort of stop mission button, but that's it. There will be no input to this whatsoever. And one of the reasons for that is that the signal takes so long to get from the asteroid belt to Earth that even if you could solve the problem with no time, in other words, immediately, and send back the signal, here is what you do, there would be a 40-minute delay. So if one of the spacecraft sends back a message, I'm about to be hit by an asteroid, well, by the time you sent the message back, I got the message, move, idiot, okay, it's 40 minutes, so the mission is gone. So you can't do that. So everything has to be done out in space, completely autonomously. I have a video, I won't show the entire video because it's quite long, but I'll show you a bit of it just to give you an idea of how this works. I should say, the first time I showed this video was at a space conference. And it was a conference up at the various space agencies. And I was the first speaker, it wasn't the keynote, I just happened to be the first speaker. And somebody at the back of the room said, I'm glad to see we're starting this conference with science fiction. Okay? So this may seem a little bit ambitious. I will point out that all of the technology exists. We need to make it cheaper, we need to make it more efficient, we need to make it better in many ways. We have time to do that. Software is typically the last thing done on a mission. Missions have to launch in specific windows to get the right gravitational pulls and paths and so on and so forth. But the software can usually be set up afterwards. It's one of the big advantages of software is you can change it in a device without pulling the device back. So you can also upload the first edition to a device. It's slower, of course, because you're sending it such a distance, but it can be done and is regularly done. So this is just to give you an idea of how this mission is intended.
This reconfigurable technology, or SMART, will contain all 1,001 kilogram spacecraft. This SMART cube will be delivered to the Earth-Moon L1 Lagrange point for deployment. Each spacecraft will be released in sequence from the SMART cube. The self-deployment of each spacecraft from its SMART shell will be the reverse of the manufacturing scenario. After deployment, the recyclable SMART shell will reconfigure into a stackable and reusable rectangle for return. Carbon nanotube tethers will be deployed to multifaceted lens nodes to form the frame for the sail. The lengthening shortening process is completely reversible, and the nodes are flexible. Thus, the frame is extensively shaped. A smart instrument and subsystem holding platform, similar in design to a space frame, will be reconfigurably tethered to the frame. The sails will reversibly deploy over the frame from specially designed lens nodes. The sail and frame are changeable in shape and extent, and are capable of forming tip vanes, making holes, and stowing sails as needed to assist in navigation and data collection. There are 10 classes of
plus communication specialists called messengers, and processing specialists called leaders. Subswarms will form and depart as groups of 100 spacecraft become available, with 10 from each specialist class. Over a period of 2.5 years, the swarm will travel on a solar sailing trajectory toward the asteroid belt. In each subswarm, imagers will perform remote detection of asteroids. Based on imager input and mission goals, leaders will select optimal targets. Each subswarm then navigates to its assigned target. Imagers collect data for a 3D model from stereo imaging, and possible inputs from other worker classes for further details near the target. Once the 3D model is adequate, clusters of workers of the same class move to optimal configurations for their data gathering operations. When leaders determine that the target has been adequately surveyed, data-taking operations cease, survey knowledge is shared, and a messenger is selected to return the data to Earth.
Won't play the rest of it because it goes on for quite a bit. But essentially there are two major threats. One is collision with other devices and with, of course, the asteroids. That's why we plan to send 1,000 spacecraft, because we expect we'll lose between 60 and 70%. Others will be damaged, so not necessarily destroyed completely, but the cameras or whatever devices they're carrying may not be of any use anymore. In that case, they can change their role. They can become a messenger, which is basically just signaling between subswarms, or it can take over the role as a ruler, which is a coordinator for the subswarm, if you like. But basically, we know that many of the devices will become inoperable or very little use to us. The other problem is solar storms. So the sun is a star, and like all stars, it is stardust. And people think this is very romantic, but stardust is basically spacecraft. Okay? So space junk that gets emitted from the sun on a regular basis. The good news is that we get about 24 hours notice because the sun's disk changes color. So we know that the storm is coming. And when this happens, we have to put the devices into sleep mode so that A, they won't be damaged by the junk that's being ejected, but also for electromechanical damage. And then when we're finished with that, they have to reopen and go back about their business. And this, to date, is the biggest problem we have in getting them to reopen. And I'll come back to that in a few minutes. So, essentially, it's a huge problem. There are many thousands of people working on this mission, as you might imagine. And so I'm just going to talk about what our contributions are in terms of software. So we're looking at it from 4 key areas. One is formal methods, another is autonomic computing, software product lines, and then automatic code generation. So in terms of formal methods, we had a project called Formal Approaches to Swarm Technologies, where we looked at the use of swarms in a number of various application areas, not just in space exploration, and tried to determine what were good methods for expressing what we needed, what were good methods for specifying and designing these types of systems. And we had it originally in mind that we would come up with some sort of a design method of our own, which would enable us to express all of this. In other words, we take the best features from multiple different approaches and bring them together in a single method. And we decided at the end of the project this didn't make sense. What we actually needed to do was have multiple different views of different aspects. And therefore we ended up using a whole range of different notations. Now some we would need in some contexts, some in others, some we would use very rarely and some we would use regularly. So we used everything from CSP, which is Force Communicating Sequential Processes, to a Milner CCS, Calculus Communicating Systems, and a probabilistic version of CCS called WSCCS. And we had big problems with that because first of all we didn't really know what the probabilities were. We were just guessing probabilities. And in many cases the probabilities were absolutely tiny. And of course when you combine tiny probabilities with tiny probabilities, you get really tiny probabilities. So much to the extent that a factor of 10,000 didn't really make a difference. So it really wasn't very useful to us. Not to say it wouldn't be very useful in other areas, but for what we were trying to do, it wasn't very, very helpful. So we ended up looking at all sorts of different notations for state changes, for communication, for distribution, and so on. And we ended up really deciding that we wanted some sort of a dashboard to all of these. In parallel with that, one of my postdocs had spent his PhD working on a specification language for autonomous systems. And he called it Autonomic System Specification Language, or ASSL. And he and I published a number of papers about it, and in particular using it within NASA. And we got an email from somebody at one stage saying they thought it was very nice that we had a programming language that had ass in its name. So, and of course, it's not a programming language, it's a specification language, but it does have primitives built in that you can run in autonomous systems, and then it can generate Java code, and it can generate efficient Java code. And I should say that NASA do use Java, but they do not use it in anything that launches. Okay, that's important.
But they use what? C?
They use C, C++, and they use a number of their own languages. People forget that NASA doesn't use standard processors. They basically get processors built for each mission, for each spacecraft. And many times they have to be low power, low weight. So in many cases, they're actually very, very primitive. So you're almost programming in assembly language. So because they have to be so light and so low power. So we've been looking at how we can exploit ideas from autonomic computing. And so many of you probably will be familiar with this, but just in case you're not, the idea is to take inspiration from the human body or the mammalian body. And there are two components to that. There's the sympathetic nervous system, the fight or flight. So this is how you protect yourself naturally. So if you touch something hot, you put your hand back automatically. You don't think about it, you just do it. So that is a way that the body protects itself. And then there's the long-term rest and digest, the long-term health and care of the body, which is the parasympathetic nervous system. So NASA has actually used some of the ideas behind this for a long, long time before the field actually came into being. IBM claimed that they invented the field of autonomic computing, but actually DARPA did about 10 years before. And IBM, if you like, resurrected it, and fair play to them for that. But we've been able to build up, if you like, an autonomic environment. So probably there should be a bit more color on this to distinguish it. But the idea is that you have autonomic elements. So you have components or managed components that you are concerned about. And these are the components that you want to be able to self-adapt in some way. In our case, for protection, basically. And so you have some sort of a manager that is monitoring this. And it was interesting, I think on Tuesday somebody mentioned the mate loop, and essentially that's what this is doing. Okay? So NASA had come up with the idea from embedded systems, of course, to have the concept of a heartbeat. But we added to this the concept of a pulse beat. So you have a signal that shows by the speed of the signal the health of the component. And by health, we mean that the component is acting the way it should do and is behaving the way it should do. So this has been used in NASA missions for about 40 years. The idea is to send a signal that gets faster as an issue becomes more important. And this signal, the speed of the signal can be picked up. And of course, because it's the speed rather than the content, the signal actually does not have much overhead. You're really sending nothing, it's just the speed of it that's important. So you can combine this idea of a heartbeat and a pulse beat to give you information about the state of your system. We can put components into a sleep mode, which we have to do for the solar storms, or if there may be some other issues. And we can then bring those components back into action again and have them stay awake. And we've developed the notion of an autonomic license, of what we call an Alice signal, whereby two components can negotiate with each other that they trust each other and they're willing to work together. And trust not just being that you're not somebody who's broken into the system, because NASA tends not to have a big issue with that, but the fact that I can trust you that you are operating and behaving the way you should do, and that your services are being provided the way I expect them to be. And of course, this then will be done across a communication channel that in itself is self-managing. And communication in space is very difficult. You've possibly heard of NASA's project to put the internet in space, where satellites and spacecraft are actually nodes on the internet. And that has been very, very successful, and is something that certainly will proceed in the future. We've been taking ideas from software product lines, and the idea is that we have multiple spacecraft in a single instance, and they're mostly the same, but they vary depending on the different devices that we give them, and therefore their software has to vary somewhat so that they can process the information that they collect in a primitive way. But also, we want to be able to use slightly different devices. So the devices that go over the rough surface of the moon or the sands of Mars are going to be rather different from the ones that fly through the rings of Saturn or that fly through the asteroid belt. But they do have to do many of the same things. So here the big red circle is showing the self-protection. So if we want to protect the devices from a solar storm, we have to put them into a sleep mode where they use their solar panel actually as a protection device. So the solar panel can protect the physical device itself. But when we go to the rings of Saturn, we don't have asteroids coming at us, so we have different issues to deal with that. And then, of course, on the surface of any planet, we have something else to do. So we can swap in and out behaviors using this idea of a future model from software product lines. And then the fourth area that we're working on is developing automatic cogeneration methods. And of course, automatic cogeneration is nothing new, but this is a newer approach to it. So the idea is that NASA engineers tend to write their requirements as scenarios. At a push, you might get them to draw something in UML, but basically they like to write English. And this has become a big problem in many cases. So we want to get code, and if we can generate appropriate models from the requirements, then we can get from the models to the code using existing tools. We can extract models from code using various tools, and there are a number of people who made a lot of money out of this in the year 2000 because of the alleged bug. But if we can reverse the mathematical laws of concurrency, so if we can take laws that describe concurrent systems and invert them, then we can generate a round-trip development process. So we've been working on this for a number of years, and we've developed a product, or if you like, a demonstrator. This shading may not be very visible at the back, but some of this is an existing prototype, some of it is using existing tools that are out there, not developed by us, and then some of it is things we're going to do in the future. But the idea is to take your scenarios and basically strip them down to be something very, very basic, and then infer a model from that. And so the model that you infer, of course, is going to be quite inefficient. So using machine learning techniques, we can actually generate something a lot more efficient, but we have, of course, multiple different instances of that. And then we can analyze this in various ways. We can see what ways we want to implement it, and then we can generate the code for the specific platform that we want to use. So we've got a lot of benefits from this. We can automate our development process. So basically, we can take scenarios from NASA engineers, and we can generate code. We have better quality, as you might expect, in that code generation. We can do formal proof of the properties of the implementation, and we can show proof of correctness from our implementation to the specification that we had. and we can do a sort of a what-if analysis, if you like, of the requirements, and we can automate this to a certain extent by trying different things and seeing what might happen. And we guarantee that the code that we generate at the end is going to correspond to the application that we had. So we've used this in a number of different applications. So obviously for end-to-end code generation and with a provably correct system. We've been looking at how we can re-implement the system after requirements changes without having to actually then, of course, regenerate the entire system. We've been looking at reuse across platforms because, as I mentioned, we use specific processors for different types of devices, for different missions, and therefore we may want to be able to implement the same thing in multiple different contexts. We've been reversing legacy systems to a model that's mathematically sound, and this is particularly true in the case of satellites, because most satellites are run by expert systems. And typically the way the expert system works is to have two versions of it running, one that monitors the system and one that runs 24 hours late. And so what it does is it monitors the system and then the next day compares the other run and sees if it would have done the same thing. And if it didn't, then it says there's something we fixed. So it's a very inefficient way of doing it, but it is a way of automating it. So the problem is a lot of the systems that are out there, a lot of the satellites that are out there, the expert systems that are being used, nobody knows what the rules are that are encoded in them. So we've been able to extract some of the rules, at least in a manner that we can understand, and we can understand then some of the decisions that were made.
Can I inject something? Such a statement, reverse engineering legacy systems,
Yes.
sounds such a holistic statement that I cannot believe it.
Well, obviously, we're using it.
So tell me what the constraints are.
Constraints?
Otherwise, banks would love to have you, and they would convert all of their legacy systems with your approaches into the modern times.
Absolutely, I agree. Well, I don't mean to make a grand statement that we can do this.
But it sounds like.
We're doing it in our application area, which is space, okay? So it's a very limited domain. I'm very much a believer in domain-specific everything.
So what is the specifics then of the domain that
So the
distinguishes from others?
Well, first of all, it's got a very limited vocabulary, if you like, okay?
Limited concepts.
Yes, there are limited things you can do. People think of space as being a very grand, difficult problem, and yes, it is, but most of the devices do very simple things. Okay? So, yes, and I'm not suggesting that we can take any old system and regenerate it, but I'm saying we can take the legacy systems that we have, extract a model from them because we understand the model once we have it, and because it's a domain we know about, then we can restructure it and we can regenerate code. I'm not suggesting it's a push button and it's all done, right?
And can you comment on selfless? The selfless model
The
what does help in mathematically?
mathematically sound. Well, that is that we're not leaving anything undefined. We can determine it's not undefined, and we're not making contradictory claims and so on.
And that reverse engineering, and then you said you generate code, you do for taking that technology in a new system, or
No, actually,
for changing the old one? Or?
for changing the old one, and because remember, most of the systems would have taken 20, 30 years to build.
Yeah.
Some of them have been running 20, 30 years. Nobody understands what's in them. Okay, so we're trying to basically document, if you like, what's in there. So not necessarily that we will change them, not necessarily that we will re-implement them, and not necessarily that we'll copy that, but just to know what's going on in there.
And what code has been that on those old systems? It's all proprietary.
Not all of it, but most of it,
Most.
yes. Yeah, and so there would have been a few later systems that might have experimented with C++ or C, and some of them would have experimented with Prolog and things like that, but most would be proprietary.
The center code.
Really a bit higher level than that. Yeah.
But no COBOL.
No COBOL.
Marco.
I cannot say for certain that they don't use COBOL in the finance department, but certainly not for anything else.
Okay, not for the technical system.
Not for the technical system. Yes.
Thank you.
Yes. So there's probably COBOL in there somewhere in some dark office down on 3rd Street, but yeah, not in anything that applies. So we've used it so far on a number of agent-based systems. We had one very interesting one. We had NASA has a lights-out operating system. So in other words, the system is untended, and the system switches itself on when the satellite is due nearby. So there are a number of stations around the world, and some of these are in the middle of the desert. And so basically what happens is when the satellite is due, the base station turns itself on, boots up, does some telemetry with the satellite, looks at various situations and decides if everything is okay or not. And if there's a problem that it cannot solve itself, it will page an engineer. Then the engineer logs on and can do things online, remotely, doesn't actually have to go out to the station. And then when the satellite is moved on, the station shuts itself down and the next one gets ready. And typically there are 6 or 8 around the world monitoring the given satellite. And we had a situation where one of the engineers was going on holiday, and so had logged in to the base station before the satellite came into control. And there was a problem that he was able to fix. And then he went off on his holidays for 2 weeks. But the rule that was built into the system was page the engineer and keep paging every 15 minutes until the engineer logs in. But the engineer was already logged in, so he didn't actually log in. So every 15 minutes for his 2 weeks of holiday, he was paged. We've been working on some wireless sensor networks, so this has been particularly for monitoring water. And you can imagine, if you like, that the ANTS mission is a wireless sensor network, just where the sensors are spacecraft instead of fairly simple devices. We've used it on the ANTS mission, as I mentioned. Again, the mission hasn't launched, but we have a number of simulations and so on of that. And we've used it on verifying initially the robotic procedures for the Hubble telescope, and then those later became the human servicing of the telescope. I don't know if you've seen the telescope or know much about it, but we have a mock-up of it in Goddard Space Flight Center. It's everything except the lenses. It's roughly the size of 3 buses. And when it was launched with these solar panels that were intended to fold up. And the idea was that the space shuttle was designed so that this fits exactly in the cargo bay. And then every 5 years, this would be taken down by the space shuttle, would have its servicing done to it, upgrades to lenses and so on, and then it would be relaunched by the space shuttle. In actual fact, when it went up, the solar panels didn't unfold, and they had to be replaced by fixed panels, and as a result, it never fit in the space shuttle. So, what had to be done was to plan how it would be serviced, how it would be updated, and this was to be a large project involving a robot arm that was what we call a dexterous arm, and then 2 grapple arms, so there's 3 components, if you like, to it. In the end, it was done by humans, but the principle was essentially the same. And what had to be done was to work out the changes that had to be made to this device over time. And so this is the first page of the instructions to update the Hubble telescope. And if it looks very like a Word document, there's a very good reason for that. It is a Word document, okay? But it's 5,000 pages of a Word document. And it took over 3 years to develop. And basically, the first column are timing constraints. The next column are the requirements of the grapple arm, which is the big arm that goes out. And of course, that would eventually become a human. And then the next 2 columns are the dexterous arms, so the 2 grip arms of the robot, which again would become a human using 2 hands. And of course, would change a little bit for a human, but the principles are mostly the same. So it took over 3 years to develop this. The problem is that the updates could only be done while you could see what was happening. And so the telescope was being watched by 3 satellites, 3 Tejas satellites. Unfortunately, one of those went out every 90 minutes for about 11 minutes. So every 90 minutes for roughly 11 minutes, you couldn't see what was happening. So you couldn't be doing anything like having cargo bays open or having lenses dangling in air or in space, I should say, or anything like that. So all of these instructions had to be recalculated when the mission began. And they had to be recalculated roughly in an hour, okay? And you didn't know where the orbit was going to be, so you couldn't do it in advance, but they had to be done pretty much within an hour of the mission launch. Or rather, the space shuttle getting to where it needed to be. So we were able to take this and tag, of course, using XML, and we were then able to input this into our own little prototype tool. Because we call the approach requirements to design to code, we use the R2D2 robot as our logo, and you can see it up in the top left. And I called Lucasfilm, and when the caller ID says NASA, Lucasfilm answered. It's great. And George Lucas gave me permission to use this. So, but not if we sold it to anyone. And we have actually now licensed it to a company that sells a major cogeneration tool, and they're using this technology, or will be using this technology, but they won't be using the robot. Anyway, we were able to generate, based on our prototype, a machine-readable version of CSP, and then we're able to execute it in Java, and we end up having this deadlock. And we kept trying this. The deadlock came after about 15, 30 seconds. And it kept happening, and one of our guys went into the code, and he couldn't see why it was happening. And eventually we discovered that there was a deadlock on the first line of the 5,000 pages of instructions. Now, it doesn't mean that they wouldn't have discovered this themselves, but it got us a lot of brownie points by being able to discover it before they did. So as I mentioned already, the next large mission that's going to be based on, from NASA, based on software, is what was originally called Constellation, and then became Orion, and then became Constellation again, and then Orion. I think it's had like 6 different names since then. But this is to be the largest software project ever. And I always try to remind people that just because we can do things nicely on paper doesn't necessarily mean it scales up. Okay? So nice things on paper may not actually work in the real world. This is my mom, who unfortunately passed away a year ago, but she got her first patent at 81 for drone technology. I overheard her on the phone telling one of her friends what I do, and I thought, that's not it at all. And then I thought a bit about what she was telling her friend. I thought, well, if we adapted it a little bit, we might get something out of it, and we got a patent. So she got her first patent at 81 years of age. She made the front page of the national newspapers. So. And NASA are now using her technology in drones. So I'm just going to finish up with a quote from David Wheeler. David Wheeler worked as a PhD student on EXAC, the machine I showed you earlier. And he's credited as being the first person to get a PhD in computer science. Not to say people didn't get PhDs in computing before that, but they were in mathematics or engineering or whatever. He was the first person that is claimed got a PhD in computer science specifically. He also invented the Wheeler jump, which we now call a subroutine. And he said that any problem in computer science can be solved with another layer of indirection, but that will usually create another problem. Thank you.
You said when you try to launch these 1,000 small spaceships, that they will organize it in subswarms, which will eventually collaborate on certain tasks.
Yes.
So is there a master plan behind? And if so, who's coordinating and enforcing it?
Like all missions, there will be a technical team, there will be a software team, there will be a science team. So the science team have what they want to get from knowledge of the asteroids, okay? So they're scientists, they're not engineers, they're not computer people. They want to know what makes up the asteroid belt, what's inside the asteroids. So they will set goals of, we're looking for this type of asteroid, so the swarm will try and find asteroids with those kind of properties. Then as they send back data, they can get new instructions as we're looking for this, we're looking for more like this or more like that. So basically it's goal-oriented, if you like.
Okay.
But it's from the scientists, not from the engineer. Yeah.
Is there an underlying operating system or anything on these devices, or just firmware and straight up your codes?
It varies over time. Like I said, we've been working on this for about 20 years. and there'll be at least 10 more years before it actually gets implemented. Right now, there isn't a specific operating system. It's using pretty much standard. It is likely that a specific chip will be developed for these, and therefore there probably will be a specific operating system for that. Depending on what the chip is, it could be a chip that's a standard chip that's adapted, or it could be something that's built specifically for it. So that's kind of a last-minute decision. The major ship will take approximately a year to get where it has to go. Then the devices will take about 2.5 years to get to the asteroid belt. So even from launch, there's 3.5 years to do the software. Believe it or not. Wolfgang.
I was impressed on page 26. So
Page 26, slide 26.
Because there you said you can guarantee the correctness so that the requirements are guaranteed to be correctly.
Well, to the extent that you can, yes, yes.
Aha.
We know the issue of this in
That
formal
means you
methods,
cannot.
yes.
Okay.
To the extent that you can, yes.
Yeah.
You have to phrase things to government people a certain way, because you put in the vagary.
But you are not talking to the government here.
That's true. But you never know when they're listening.
Very carefully.
Do you have more questions? No? If not, let's thank the speaker very much. I assume there are a few announcements.
Yes, absolutely.